Hello and welcome to INE's CCI Service Provider version 5 lab course. Today we will learn about OSPF and deep dive into the different types of LSAs of OSPF. For some of you who do not know me, my name is Rohit Pardasani and I would be your instructor throughout this course. I have 5 CCIs, CCI in route switch, CCI in security, CCI voice, CCI collaboration, and CCI service provider. So let's quickly deep dive into OSPF LSAs. So let's first look at how do we configure OSPF on a Cisco IOS XE and Cisco IOS XR. So here is how you would configure OSPF. So we can define by saying router OSPF1, which is an OSPFv2. It only supports address family for IPv4. If you want IPv6, you can run a separate OSPF process with IPv6 router OSPF. However, if you want both the address families running together, you can run OSPFv3, which we would be discussing later on. So configuring OSPF on an iOS XE versus iOS XR-V, it's not very different. It's pretty much the same thing. It's just that on an iOS XE, you would go to the interface and activate OSPF, or you could use the network statement under OSPF protocol and activate OSPF. As far as the XR-V is concerned, you define OSPF or you create OSPF process and you define the area and you activate OSPF on the interface, but not on the physical interface, but inside the process. To verify your adjacency, you can always give the command show IP OSPF neighbor. This basically tells you the router ID of your neighbor, the interface on which you're establishing the neighborship, the IP address of your neighbor, the priority of the neighbor. If you remember, the priority is used when you have a broadcast segment. So if there's a DR election, the default priority on a Cisco router is by default 1. Higher is better. Highest can be 255, and if you set that to 0, it does not participate in DR election. Besides that, you can also look at the state for OSPF. As you know that OSPF has different stages of a neighbor establishment. It basically starts with init packet, where you are sending a hello packet saying, hey, I am router ID 1.1.1.1. Then the neighbor will respond back saying, hi, 1.1.1.1, I am 2.2.2.2. That's your two-way state. Then we have your X start, where router 1 would say, hey, I'm going to send you my database information first. And router 2 would say, I am a higher router ID, so I would exchange first. That's at your X start state. Then we have the exchange, where they start exchanging their database. And then we have the loading, your SPF is calculated, and then we finally have the full state. If you look at the show IP OSPF neighbor output, you can always look at the state at which your neighbor is at. Verifying the adjacency on a Cisco IOS XR-V is pretty much similar to iOS XE. We just issue the command show OSPF neighbor, and that would give you the exact same information that you would see on a Cisco iOS XE. So let's look at the database. Verifying the database on a Cisco IOS XE or an XR-V is pretty much again the same. We can look at your router LSAs or network LSAs. If you have a DR segment, it gives you all the information about all the prefixes learned from that neighbor. It also gives you information about the metrics on each of the interface. So we will actually deep dive into all of the different types of LSAs that we need to learn for the CCI service provider. Obviously, not all LSAs are going to be used. You would probably use just a few of them. You would not be looking at LSA 5 or maybe LSA 7 in the CCI service provider exam. You would probably be tested for just LSA 1, 2, maybe 3, maybe 4 if you're doing some kind of redistribution, 4 and 5, but you would never have any questions about stub or totally stub or not so stubby. So you may have 5 if you're doing redistribution, but you would not have a separate question on LSAs. So looking at the database, if you want to verify your database, you can always do a show IP OSPF database and look at all the information, or you could do a show IP OSPF database router that shows you your router LSA, or a show IP OSPF database network that shows you LSA2, which is your network LSA. Looking at your iOS XRV, the command is pretty much the same. Instead of show IP, we give the command show OSPF database. Obviously, you already know how do you verify your routing table. You can do a show IP route OSPF that gives you all the OSPF routes. If the routes are intra-area routes, they would be seen as O. If the routes are inter-area, they would be seen as OIA. So what we need to understand now is all the different types of LSAs, even though some of them we would not be using for CCI's service provider, but we would still be discussing them just for your information. So if you look at OSPF, OSPF has different types of LSAs. Mainly there are 11 different types of LSAs that you can configure or look at, and look at the differences between all of the LSAs. The first one is the router LSA, which is LSA1. Then we have network LSA. We have summary LSA, which is LSA3. We have ASBR summary, which is LSA4. We have LSA5, which is external LSA. We have LSA6, which is group membership LSA. We have LSA7, which is not so stubby area external LSAs. Then we have LSA8, which is external attributes LSA. LSA 9, 10, and 11, they're basically used for, they're basically opaque LSAs, used for link scope or intra-area LSAs. They're used for area scope, or they're used for AS, autonomous system scope. We will discuss this in depth in the next slide. So let's understand each one of this LSA. Let's try and understand them and see where it is used and how does it work in OSPF. So the first one we're going to look at is router LSA, LSA1. Now LSA1, like I said, it's called as router LSAs. The packets are sent between routers within the same area of origin and do not leave the area. An OSPF router uses LSA type 1 packets to describe its own interfaces, but also carries information about its neighbors to adjacent routers in the same area. What this basically means that, let's say if I have 2 or maybe 3 routers in the same area. Let's say maybe I have router 1, 2, and 3, they're all in the same area. Let's say area 1. Router 1, if he has to advertise all of its networks, all of its interfaces which has OSPF enabled, if he has to advertise that, he basically sends LSA1 to router 2. Now router 2 receives LSA1 prefix, and when router 2 has to advertise that to router 3, he would basically add that information. He would send that information to router 3 unchanged. The LSA does not change within the area. It does not change at all. It does not change. So what's going to happen is that whatever LSA router 1 generated, that LSA remains the same throughout the area, within that area. It remains exactly the same. The information does not change. The first thumb rule of OSPF is what? It is that everybody maintains the exact same copy of the information within the area. Everybody maintains that. So the information cannot change. That breaks the rule of OSPF. So here, router 1 and router 2 are basically exchanging LSAs, LSA1, which tells them their information or their specific interfaces with the metrics that they have. So let's in fact see LSA1 in action. What I'm going to do here is I will build a topology where I would have some routers. Maybe I have router 1 which connects to router 2. Then I have router 3. I have router 6. I have XR1. And then finally I have XR2. I'll put all of these routers in one area, maybe area 1. It does not need to be in area 0. Area 0 only has a significant role when you have multi-area. Otherwise, you could have just area 1. I'll just put all of these routers in area 1. And what I would do right now to eliminate your broadcast segment or to eliminate LSA2, because LSA2 only gets generated when you have a broadcast segment. What I'm going to do is I would convert all of these routers, all of the links on these routers to be a point-to-point link, so only LSA1 would be generated. Remember, LSA1 does not get flooded outside the area. It's only within the area. It cannot cross the border. However, LSA1 remains unchanged throughout the area. It remains unchanged. It does not change. So as soon as router 1 starts advertising his prefixes as LSA1 to router 2 adds that information in his database, and then he forwards that LSA1 again to R3. However, he does not change anything in the LSA. The LSA remains exactly unchanged, exactly the same how R1 had originated it. So let's look at this. What I'm going to do now is configure all of these routers to basically run OSPF, and at the same time we would see the database, look at how LSA1 works. You would see that LSA1 does not go outside the area. So let's start with router 1. So we'll do a router OSPF1. Let's set the router ID to 1.1.1.1. Router ID has to be unique within the area. And let's do network 0.0.0.255.255.255.255 area 1. Let's go to router 2 and run OSPF here also. So router OSPF1, router ID 2.2.2.2, and then network 0.0.0.255.255.255.255 area 1. Let's go to router 3. So I'm basically disabling OSPF because I had configured OSPF earlier for some other tasks. So I'm going to disable that. So no router OSPF1. Router OSPF1 router ID would be 3.3.3.3, and then I have my network statement, which basically activates OSPF on all my interfaces. We have router 5. Router OSPF1 router ID would be 5555, and then we have our network statement which activates OSPF. Then we have 6. So router OSPF1 router ID would be 6666, and network statement. Let's in fact remove OSPF process first and re-add the process, router ID, and my network statement. Finally, I have XR1. So router OSPF1 router ID would be, let's say, 19.19.19.19. Address family IPv4 unicast. Area 1 and interface would be gig 0x0x0x0.1920 and 619, and finally my loopback. Lastly, I have XR2. So router OSPF1 router ID would be 20.20.20.20. Address family IPv4 unicast, and finally area 1. Interface loopback 0 and interface gig 0.0.0.1920. So at this point of time, all of these routers, router 1, router 2, router 3, router 6, XR1, XR2, router 5, they all are in area 1. So if I do a show IP route OSPF, I should see all the OSPF routes as intra area. They should establish OSPF neighborship. Let's verify that. Show OSPF neighbor. So it's still coming up. Right now it's in two-way state, which you can see here. And there is a DR election happening. I haven't changed my interface to be point-to-point at this point of time. So they still have a broadcast segment on all of its links. So there would be a DR election and there would be LSA2 also. So let's wait for the neighborship to come up. Now my neighborship has come up, and if I do a show route OSPF, I should see all my routes in my routing table, and they are seen as O, which is intra-area, and these are basically advertised using LSA1. So let's verify our database. Show OSPF database. If I just do a show OSPF database, you would see all your LSAs. So since I don't have inter-area right now, I would not see LSA3, or I don't have an ASBR, so I won't see LSA4 or 5. Right now, I would only see intra-area LSA, which is LSA1, router LSA, which contains my prefixes. And because I have a broadcast segment and there is a DR present, I would see LSA2, which is my network LSA. So, which is what I see here right now. I see router LSA, I see network LSA. So let's in fact eliminate the network LSA. We don't need that right now. We don't need that. I would set all my interfaces to be point-to-point. And at that point of time, I would only see LSA1. So let's go to our routers and set our interfaces to be point-to-point. So gig 1.12, IP OSPF network, point-to-point. Obviously, your hello and dead and your network type should be same, otherwise you would not establish neighborship. So I've actually lost my neighborship with router 2. It actually goes down and comes back up, but it would not be stable because one side has a DR and the other side does not have a DR. So let's set R2 also to be point-to-point. So interface gig 1.12, IP OSPF network point-to-point, gig 1.23, which is towards R3, and towards R5 to be point-to-point. Let's change R3 as well. So interface gig 1.23, IP OSPF network point-to-point, and interface gig 1.36 would be point-to-point, and gig 1.34 would also be point-to-point. Let's set R5, gig 1.25 to be IP OSPF network, point-to-point. I have R6. And finally, XR1. XR1 is configured differently. So it's not done under the physical interface, like how in iOS XZ we go to the interface, the physical interface, and we apply the network type. However, in iOS XR, we actually go to the interface, but not on the physical interface, but interface under the process. So let's go back to router OSPF1 under area 1. And we should go under interface 619, and here I would set the network type to be point-to-point. So network point-to-point. Same thing for interface 1920, network type would be point-to-point. Let's commit. And same thing on XR2. So router OSPF1, area 1, interface gig 0000.1920, network would be point-to-point. So now that I have implemented OSPF area 1, single area on all these routers, I have changed my network type to be point-to-point. There should not be any LSA2. So let's look at our routing table first. Show route OSPF. So I still have all my routes in my routing table. If I do a show OSPF database, I should not see LSA2 now, which you can see that there's no LSA2 or network LSAs anymore because there are no DRs. There is no DR on any of my segments within the area, so there would not be any DR election, so there's no need for LSA2. It's only LSA1. Now let's look at how LSA1 is advertised and does it change within the area. So we'll look at one prefix. Let's say router 1 is advertising an LSA prefix, maybe his loopback. So if I do a show IP OSPF database router LSA and do a self-originate, what LSA is router 1 advertising? So if I do a self-originate, you would see that router 1 generates one LSA. That one LSA1 contains all the list of links that he has. How many links does R1 have? He has one loopback and one link that connects to router 2. So this is what we see here, that I see the loopback and I see the network that connects to router 2, and here is where I see the metric of that connected link. So the link between router 1 and router 2 has a metric of 1, and the neighbor router ID is 2.2.2.2. Now let's look at this LSA sequence number and the checksum value. The whole concept of checksum is for what? Is to basically identify that or to confirm that the LSA hasn't changed, it hasn't been compromised. So what's the checksum value for the LSA that router 1 has generated? I see 8943. Now let's look at XR2, which is the extreme other end, and do a show IP OSPF database. In fact, it's show OSPF database router LSA 1.1.1.1. So if I see now, I see the same checksum value. Or if I even do a show OSPF database router without even specifying the router ID of R1, I would see all the LSAs of all the routers, but if I look at who has generated the network 1.1.1.1, the network 1.1.1.1 was advertised by the router ID 1.1.1.1. Now this is different and this is different. This is the prefix and this is the router ID of the device, the name of the router. Let me in fact go to router 1 and change his router ID so that we can look at the database again. So router OSPF1, router ID, let's set this to 11.11.11.11. And let's do a clear IP OSPF process. And let's look at our database again. So if I do a show IP OSPF database router and scroll all the way back up, you would see that it was generated. So 1.1.1.1 prefix was generated by the router ID 11.11.11.11. So he's the advertising router. And look at the checksum 8CEE. And if I look at router 1 and do a show IP OSPF database self-originate, he's generating 8CEE. So this basically proves that LSA1 does not change within the area. It remains the same within the area. Yes, between areas, the ABR is going to change that to LSA3, but area 1 LSA or intra-area LSAs, LSA1 does not change within the area. Everybody has the exact same copy of the information. This is LSA1. So LSA1 contains what? It contains list of all the links that a router has. So if I am sending an LSA1 to you, I would send you one LSA, which is LSA1. So I'm not sending multiple LSAs for each link. I would send one LSA, which contains list of all the links that I have and the cost for all the links. So I will send that to you. You would send that information, you would add that information to your database, and then you would send that information to your neighbor. Unchanged. You don't change anything. So every router would see exactly the same thing, that this prefix is basically generated, or it is hosted by this router ID. Everybody has the exact same copy. So LSA1 is a prefix information. It's not router ID information. It's basically a prefix. It contains list of all the prefixes with the metrics and the neighbor's router ID. So if you look at LSA2, which is the network LSA, the packets are generated by the designated router, which is a DR, to describe all routers connected on that segment. LSA2 packets are flooded between neighbors in the same area of origin and remain within the area. Again, LSA2 does not go outside your area. It's only contained within the area. LSA2 is not a prefix information. LSA2 only contains a list of connected routers in that segment. So let's in fact now see when LSA2 is going to be generated. So what I'm going to do is take the same network that we had earlier, where we had router 1, 2, 3, 6, 5, XR1 and XR2. They all were connected in area 1. But however, if you remember, we had changed the network type to point-to-point. This time I would change it back to be broadcast segment. Any one of the interface, I would change it back to broadcast segment. So let's go back to our routers. What I'm going to do is maybe the link between 2 and 3, I'll change that to be broadcast segment, just that link. So the minute I change that to a broadcast segment, a DR gets elected, which means LSA2 is going to be generated. So let's go back to router 2, interface gig 1.23, IP OSPF network broadcast. Same thing on R3, interface gig 1.23, IP OSPF network as broadcast. I'll also change it between XR1 and XR2. So all my remaining links are still point-to-point. Just the link between 2 and 3 and XR1 and XR2, they have basically changed to be broadcast segment. So let's go back to XR1. And here I would say interface gig 0000 1920 and network would be broadcast. Similarly on XR2, router OSPF1, area 1, interface gig 0000 1920, network type would be broadcast. Let's now verify. So if I look at router 1 now and do a show IP OSPF database, this time router 1 would see LSA1 and LSA2. Why am I seeing LSA2? Because there are two DRs. There's one DR for the segment between 2 and 3, and there's one DR for the segment between XR1 and XR2. So he would now see LSA2 prefix or LSA2 as well. So going back here, I should see one more between XR1 and XR2. It should come up in some time. Right now I'm seeing it between 2 and 3. And let's go back to XR1 and do a show OSPF neighbor. It has come up. So I should be able to see. Let's go to R5 and do a show IP OSPF database. So now I see both of them. Even router 1 should see both of them in its database. So he sees that there are two DRs in area 1. One is for the segment between router 2 and 3, and one is for the segment between XR1 and XR2. Now, how is the DR selected? The DR is selected based on the priority. If the priority is same, which is by default same, which is 1 by default. If it is same, it goes to the router ID. Whichever device has the highest router ID wins. So between R2 and R3, R3 has a higher router ID, so R3 wins and he becomes a DR. Between XR1 and XR2, XR2 has a higher router ID, which is 20.20.20.20, so XR2 becomes the DR. Now, how are these LSAs going to be advertised? So let's again go back to router 1 and look at show IP OSPF database, router LSA, self-originate. As you can see, router 1 is generating LSA1, and this is his checksum value. That does not basically change within the area. That would remain exactly the same. So LSA1, nothing changes. So again, show OSPF database, router LSA. If I look at the prefix 1.1.1.1, that was basically advertised by 11, and the checksum value is still the same. So that does not really change at all. LSA1 does not change. But what's the difference? The difference is, earlier, router 1 was advertising to router 2. So basically my topology was like this. I have router 1, which is a point-to-point link to router 2. Then there was a broadcast segment which connects to router 3. I had a point-to-point to 6. I had a point-to-point to XR1. And I had a broadcast segment to XR2. Now, when router 1 advertises to router 2, that's basically sent as LSA1. Router 2, when it was point-to-point, router 2 would send LSA1 to R3. However, because now there's a DR, router 2 does not send to R3 directly. Always think of the DR as a separate router. So think of the DR, even though R3 is the DR, but think of it as a separate router. So this is DR R3. So basically what's going to happen is that router 2 does not send LSA1 to R3. He's actually sending it to the DR, which is LSA1, and it's the DR who basically sends it to this router. So that's why now we have the network LSA, which basically tells the routers that on this segment I have two routers connected, which is R2 and R3. Remember that the network LSA is not a prefix. It is basically just router ID information of the devices connected in that on that interface or that segment. Similarly, here you would see LSA1, you would see LSA1, and again XR1 would not send LSA1 to XR2 directly. He would send it to a DR, which is LSA1, and that's the DR who basically advertises to the routers. So the DR segment or the broadcast segment would basically contain a DR. DR has to be present. If there is no DR elected, then obviously the neighborship would not be able to establish as full state. It would be stuck at two-way state. So let's go back to router 2. And if I go to router 2 and do a show IP OSPF database, network LSA, self-originate, R2 is not generating any LSA2. Why? Because he's not the DR on that segment. If you remember, R3 was the DR because he had a higher router ID. Show IP OSPF database, network self-originate, R3 was the DR for that segment. So he advertises LSA2 and tells everyone that on this segment, which is between 2 and 3, on this segment, I am the DR, and these are the list of routers which are connected on that segment. So this is basically LSA2. LSA1 and LSA2, they both are contained within the area. They do not go outside the area. Now LSA3, which is the summary LSA, these packets are generated only by the ABR, Area Border Router. They are basically used to summarize its directly connected area and also used to advertise inter-area router information to other areas that the ABR may be connected to. LSA type 3 packets are flooded throughout the OSPF domain. However, it changes at every border. So if you look at this diagram here, I have router 1 who basically sends LSA1 within area 1. Once it reaches the ABR is going to block LSA1 and he generates a new LSA, which is LSA3. The LSA3 would remain exactly the same within area 0. So everybody, all the routers in area 0 would have the exact same information. However, when it crosses the border again, R3, which is the ABR, when he sends that route or that prefix to area 2, he modifies the LSA and he puts himself as the originator and he forwards LSA3 within area 2. Again, in area 2, everybody would maintain the exact same information. So for area 2, the LSA3 came from R3. For area 0, LSA3 came from R2. For area 1, the LSA1 came from router 1. So let's in fact do this. What I would do is, based on our topology which we had configured earlier, so I believe we had router 1, router 2, which were point-to-point connection. Then we had a broadcast segment, router 3, we had R6, we had XR1, and then we had another broadcast segment which was XR2, and now I will connect another router here which is going to be router 10, and this would be area 0, the backbone area. I would keep this as area 1, so this would still be area 1, but XR2 would connect to router 10, which would be in the backbone area. So who becomes the ABR now? XR2 would be the ABR, and XR2 would block LSA1. He would not allow LSA1 to go from area 1 to area 0. Instead, he would send LSA3 as a summary LSA, and he would send all the prefixes of area 1 to area 0 as LSA3. So let's in fact see this. So I'm going to go back to XR1, or in fact XR2, and activate OSPF on my other interface. Let's do a show run interface. I believe I have an interface that connects to router 10. So let's go to router OSPF1, area 0, and interface gig 0000 1020. So I've activated OSPF, and let's change the network type to point-to-point and commit. Let's go to router 10 and configure OSPF. So router OSPF1, router ID would be 10101010, and network 0000.255.255.255.255, area 0. So now R10 and XR2 should establish OSPF adjacency. They should establish OSPF adjacency, and once they form the neighborship, router 10 should see all the routes of the entire domain, all the routes of area 1, all the routes of area 0. It should see all those routes. The area 0 routes would be seen as O, which is intra-area routes. Area 1 routes would be seen as OIA, which is OSPF inter-area routes. So it's still coming up. Let's wait. So my neighborship just came up, so show IP route OSPF. I should see all the routes in my routing table now. If I look back at XR2, XR2 should generate, in fact I have to change my network type. Right now there's a problem of network type because I had changed the network type on XR2 to point-to-point, but I did not change that on R10. So it's basically an issue of network type mismatch. So let's go back to router 10, gig 1.1020, and IP OSPF network point-to-point. So my neighborship should again come back up. Show IP OSPF neighbor. My neighborship is back up. Show IP route OSPF. I should have all the routes now in my routing table, which I do, and they are seen as OIA, which is OSPF inter-area. If I do now a show IP OSPF database and hit enter, you would see LSA1, router LSA for area 0, and you don't see LSA2 because the link between router 10 and XR2, that's basically a point-to-point, and the other area 1 has some DRs, but that information is not sent outside the area. So by this we can confirm that LSA2 does not go outside the area, because we had some DRs. We had a DR between R2 and R3, and we had another DR between XR1 and XR2. However, that DR information or LSA2 information was not sent by XR2 to router 10, because router 10 belongs to area 0. So LSA2 does not go outside the area. Now let's try and confirm about LSA1. Does LSA1 go outside the area? If I do a show IP OSPF database router LSA, look at what LSA1 information I have in my database. So I have information about 10.10.10.10, which is my network, and that's pretty much about it. I don't have much information. I have no information about LSA1 about other areas. So if you look at my database for LSA1, it just contains the link between XR1 and the link between XR2 and R10, which is this link, and router 10's loopback, which is in area 0. It does not contain any information about area 1. So router LSA does not go outside the area. So how does R10 get the routes? Basically, he gets LSA3. So if you see here, your summary LSA in area 0, advertising router was XR2. So XR2 generates LSA3 summary prefix, which you can see here by doing a show OSPF database summary LSA self-originate. So he generates all of these summary LSAs for area 0. So towards area 0, he sends all the prefixes. So he sends 2360, 2340, the loopbacks, which you'll see here, 1919, 6666. He's sending all the loopbacks also. So if you look at from a diagram perspective, we had router 1 who sends to router 2 LSA 1. Router 2 was sending it to a DR. So he was sending it down to a DR, which was again LSA 1. This guy sends it here. R3 sends to R6 LSA 1. And this is going down here to XR1. Again, that's LSA 1. Here it goes to a DR. So XR2, I have a DR here, which is LSA1. It's the DR who sends to this router. And now XR2 blocks that LSA1. And to router 10, he sends LSA3. So he sends LSA3 instead of LSA1. So LSA1 basically gets blocked. Now this is LSA3, which is inter-area LSAs. So if a router receives LSA1 and LSA3 for the same prefix, which one would he prefer? Obviously LSA1. So O routes are preferred over OIA. So let's look at LSA4. So LSA4 is ASBR summary LSA, and these LSAs are generated by the ABR, which basically tells all the routers in OSPF that there's an ASBR present in some area. So if you look at this example below where we have a diagram, R2 is the ABR and R3 is also an ABR for area 0. Now, router 1, who's also an ASBR, he connects to some other domain, basically BGP, and he's redistributing those BGP routes in OSPF. So router 1 becomes the ASBR. As soon as router 1 starts generating LSA5, which is basically he starts advertising his prefix, when router 2 gets a type 5 LSA, he generates an LSA4 and he advertises that LSA4 in area 0. LSA4 is not a prefix information. LSA4 only contains router ID of the ASBR, basically telling every other router in OSPF that how do you get to this ASBR? If you want to go to this ASBR, come to me, I'm the ABR, to get to that ASBR. Again, like LSA3, LSA4 also changes at every border. So R3, when he advertises LSA4 in area 2, he changes the LSA and he puts himself as the originator and sends that LSA across to area 2. Everybody in area 2 would see R3 as the originator of LSA4. Everybody in area 0 would see R2 as the originator for LSA4. In area 1, you would not see LSA4 in area 1. Now, the next one was LSA5. LSA5 is external LSA. These packets are generated by the ASBR, and that does not change throughout the OSPF domain. If you look at this diagram, router 1, who's the ASBR, he generates LSA5, and LSA5 goes unchanged throughout the OSPF domain. So if I look at R4's database, he would see that the originator of LSA5 is not R3, it would be R1, because LSA5 does not change throughout the OSPF domain. LSA5 is a prefix information. All these prefixes are represented in the routing table as OE1 or OE2. Default is OE2. The difference is that in OE2, it looks at just the redistribution cost, does not look at the OSPF cost. OE1 looks at OSPF cost plus redistribution cost. Technically, both OE1 and OE2 are pretty much the same thing, because OE2 adds forward metric, so that becomes OSPF cost plus redistribution cost. However, cosmetically, E2 only shows you 20 in the routing table, but OE1 would show you OSPF cost plus redistribution cost in the routing table. Which one is preferred between the two? OE1 is preferred over OE2. So let's in fact implement this and see our database. So what I'm going to do is I would go to one of the router, let's say router 10, and I will create a loopback and advertise that loopback in OSPF. So let's go first to router OSPF. I'll remove this network statement and be more specific with my network statement, because I don't want to advertise my new loopback as OSPF. I want to redistribute that. So let's go and remove this and re-add this with 2010 or 0.0.0.255 area 0. And network 10.10.10.10.0.0.0.0 area 0. So now I have OSPF running on just two interfaces. So if I do a show IP OSPF interface brief, I'm running OSPF only on these two interfaces. Let's create a new loopback. Let's say loopback 10. And give the IP address as 123.123.123.123.255.255.255.255, and go back to OSPF and say redistribute connected subnets. I don't have to define the metric, because by default OSPF has a metric of 20. Unless it's BGP. BGP has a metric of 1. If you redistribute BGP into OSPF, the default metric is 1. But if you redistribute any other protocol into OSPF, the default metric is 20. I don't have to specify the metric type also. Default is E2. So I can just hit enter. And now R10 becomes an ASBR. So he starts generating type 5 LSA. So if I do a show IP OSPF database, ASBR, summary, and do self-originate, he is not generating any LSA4. ASBR does not generate LSA4. It's the ABR. Is R10 an ABR? No. XR2 was an ABR. So R10, who's only an ASBR, he would only generate LSA5. So that's going to be external self-originate. So he generates LSA5, and this LSA does not change throughout the OSPF domain. So if I look back at the checksum value 8AFF, and if I look back at the extreme end R1, who's in area 1, and do a show IP OSPF database external, you would see the same checksum value 8AFF, which basically means that your LSA5 did not change. Basically, what's happening is, if you look at it from a diagram perspective, we had router 1, we had 2, we had 3, we had 6, we had XR1, we had XR2, and we had R10. So this was area 0. I believe this was area 1. And there was some route which was here, which was basically redistributed into OSPF. So now R10 is going to be my ASBR. So he is ASBR. Let's write it here, ASBR. So R10 generates LSA5. So this is LSA5. LSA5 goes unchanged throughout OSPF domain. It goes unchanged. So everywhere you would see LSA5, it remains unchanged. It's not that XR2 would generate a new LSA5 and change anything. No. It's like LSA1. LSA1 is the same within area 0 or within the area. It's the same thing. LSA5 is same but not within an area. It's same within the entire OSPF. So it's same across all areas. LSA5 does not change. It is flooded throughout the OSPF domain. However, XR2 will generate an LSA4. So XR2 is going to start an LSA4, and this would remain same throughout area 1. There's no other ABR here, so it would not change anywhere in area 1. So LSA4 is going to be generated by XR2, which you can see if I go back to XR2 and do a show OSPF database ASBR summary self-originate. He is the one who's generating LSA4, telling everyone that there is an ASBR present whose router ID is 10.10.10.10, and I am the advertising router, that if you want to reach this ASBR, come to me because I connect to that ASBR. So LSA4 is not a prefix information. LSA4 is only router ID information of the ASBR. Who generates that? Just the ABR. LSA5 is prefix information which is generated by the ASBR, and that remains unchanged throughout the OSPF domain. Now LSA6 is a group membership LSA. Basically, these packets were designed for multicast OSPF, a protocol that supports multicast routing through OSPF. Multicast OSPF is not supported by Cisco and is not widely used. It is expected to be retired soon. LSA7, which is not so stubby area external LSAs, these packets are used for some special area types that do not allow external distributed routes to go through that area. For example, an area that does not allow or permit an ASBR within that area, maybe for reducing the amount of LSAs. In that case, we could configure that area as not so stubby area, and instead of type 5 LSA, you would now see that the ASBR generates type 7 LSA. Type 7 LSA does not go outside your area. It's only contained within the NSSA area. Instead, the ABR of that NSSA area generates a type 5 LSA, so he translates type 7 to type 5 and sends that across to all the other areas. So if you look at this diagram, I have an ASBR which is generating type 7 LSA instead of type 5 because area 1 has been configured as not so stubby. As soon as R2, the ABR, receives type 7 LSA, he translates type 5 or he translates type 7 to type 5 and sends it across to area 0. Type 5 LSA remains unchanged throughout the OSPF domain. Then we have LSA8. LSA8 is external attributes LSA, which is basically used for OSPF version 2, link local LSA for OSPF version 3. So these LSAs are basically used to transit BGP attributes through an OSPF network while BGP destinations are conveyed via LSA type 5 packets. However, this feature isn't supported by most routers. With OSPF version 3, which is IPv6, LSA8 is redefined to carry IPv6 information through OSPF network. LSA 9, 10 and 11 These are basically opaque LSAs. So LSA 9 in OSPF version 2 is defined as link scope opaque LSA for carrying OSPF information. For OSPF version 3, it was redefined to handle communication prefix for a special area type called stub area. LSA type 10 packets are used to flood OSPF information through other area routers, even if the routers do not process this information in order to extend OSPF functionality. This is mainly used for traffic engineering to advertise MPLS and other protocols. So if you look at LSA type 10, this would mainly be used, or it would come in play when you have MPLS traffic engineering configured. LSA type 11 packets serve the same purpose as LSA type 10 packets, but are not flooded into stubby areas. So the only difference between LSA 10 and LSA 11 is that LSA 11 is not flooded in stubby areas. LSA 10 goes everywhere. As long as you have MPLS traffic engineering configured, LSA 10 would be generated. I hope this video was informative to you, and thank you for viewing.